Good morning, everyone. Thank you very much for the kind invitation. I would have really liked to be with you today in Porto, but unfortunately I cannot be there, so I'm delivering this keynote online. And the title I've selected is Machine Learning and Structural Design Shooting for the Moon. And it actually has these two parts. A first part where I'm going to be discussing in general the influence and the potential for the use of AI technologies in structural engineering, and particularly in structural design. And second, a case study where we have been using some of these tools for the provision of optimal arch shapes for extraterrestrial shielding structures in the moon. So the bulk of the first part actually comes directly from this paper that I wrote for the Frontiers in Built Environments journal at the invitation of Professor Takewaki over a year ago. And when Professor Takewaki invites me to write this overview paper, I actually felt the convergence of two trends. The first related to the push for automation driven by artificial intelligence in the area of structural design and structural engineering. And the second related to thinking about the way we train structural engineers today and the way we should be training the next generation of structural engineers. So if you're interested, you are welcome to download this paper. Is free online. And it starts with this issue of automation and the push that industry has always to try to be more efficient and so on. And there is this natural apprehension always when we talk about automation in the concern that the machine is going to take our jobs, right? And I think that's very nicely depicted in this illustration by Andrew Ray. But is it really the case? One would ask, and how much of our technical skills are actually going to be able to be replicated by the machine? And you can see here, this is a video coming from the research of Professor Xingzhen Lu from Tsinghua, where he just takes all the architectural input, right, and uses some AI algorithms to distinguish those spaces where you can place lateral resisting elements, namely shear walls, for example. And not only that, but using machine learning tools, he also develops an algorithm that will be able to optimize the distribution of those shear walls. And then produce the design of those, the design of the slabs, the quantities of materials and drawings. So it's basically automatizing most of the work that is done currently in structural engineering offices for relatively standard projects. The second tendency that I was mentioning before is related to the value of our degrees and the questioning of the quality of the degrees in the context of great inflation and so on. And this slide or this figure on the left was taken actually by me from the inaugural address from the incoming president of the Institution of Structural Engineers in 2019. But it's a tendency that has been argued before and also afterwards him. So here, basically, what we are seeing is this argument for a new way in which we should teach structural engineering, where we should place less emphasis on the analytical skills and probably more on the soft skills and the creativity aspects of the degree. Because it was felt that we should leave to the machine what the machine is good at, and the computers are good at computations. Well, I would argue that we can also use the machine to increase the creativity of structural engineers, and we will see some ways in which that's done. But in fact, structural engineer engineering has been benefiting from the application of machine learning for a while now. This is a slide that is taken from the research of Professor Burton, a paper from Professor Burton from California, where you can see that machine learning is being used for the prediction of structural performance, all the way up to the development of health monitoring techniques and field reconnaissance and so on. So it's actually there. It has been there for a while now. Let's try to set the language here. Let's try to define the terms, starting with artificial intelligence. And we will say that artificial intelligence is the branch of science that is concerned with the recreation of human cognitive functions. That is usually done through digital computers, but not necessarily. So there are some efforts that are nowadays employing, for example, biological tools to try to replicate this human intelligence. And machine learning is a branch within AI whose central advantage is the potential to automatically detect patterns in data. And this is really, really a big theme today. This is a scheme that I propose for the classification of machine learning algorithms, but there are many more, many more or many other proposals. And you have the ML algorithms starting with the simplest linear regression, polynomial regression, all going all the way to unsupervised learning, reinforcement learning, and so on. Yeah. But the main difference between a traditional code and an AI code, it's actually highlighted in this graph where there is a comparison, or I'm presenting a comparison in the way traditional AI software and the more conventional software operates. So in a traditional piece of software, the coder will write a comprehensive set of rules, and it's therefore the sole responsibility of whomever is coding or the programmer to consider all the potential scenarios and to hard code those into the machine, right? So it should be possible in principle to arrive to the precise output by following the path, that and the rules that have been set out at the beginning. By contrast, in AI algorithms, the rules are going to be created as an output. So what the coder does is provide scaffolding, and that scaffolding is going to be filled with the different training phases. So once those rules are established, though, they can be used in the same way as you use in a traditional algorithm to get a desired output. So what we will input for an AI algorithm or to an AI algorithm will be a series of labeled data points that from where the algorithm will be able to infer the rules itself. Now, the fact that the coder is here exempt from considering and including all the potential scenarios makes these codes very, very powerful, especially when we are dealing with large databases and complex processes. Yeah. So this is, I think, the main difference between the two. Let me now come to the case study, and I will discuss these issues with creativity and engineering intuition at the end. But this comes from a work that was done by Tom with the joint supervision of myself, Georgos, and Nikos, where we tried to propose algorithms for the optimization of shielding structures. And first, I'm going to be presenting the mechanical reasoning, and then we are going to be looking at the AI phase of it. And all of that is obviously motivated by this increase in attention and focus for spatial tourism and so on, that is illustrated by this phrase of James Ballard that says that the number of astronauts who have gone into orbit after all this expenditure is just too small, to the point of being ludicrous. And that really sums it all up. You cannot have a real space age from which 99.999% of the human race is excluded, right? So this is important, and there have been many proposals, and there are many calls now pushed by NASA, for example, a lot of funding now given for the creation of first lunar habitats, with a view to take that as an intermediate step to go then to Mars. And this is one of those proposals, in this case for Mars, that was ideated by Marsha. And you can see these very interesting structures. But more importantly, at the back, you can see the way in which those structures are being constructed, basically by means of 3D printing. And the reason is important because we have very important constraints in space, where we have extreme temperature variations, we have radiation, so you cannot spend more, a large amount of time outside. You need thick walls to prevent you dying from radiation within your stay there. There is in the moon, in particular, a lack of atmosphere and pressure, and so on. And constructing in those conditions is extremely expensive, and we don't have, the materials that we have on Earth. So what we are going to be doing is trying to use what NASA calls in situ resource utilization, which is basically trying to build with whatever you find there in the moon. And those structures need to be able to resist all these extreme variations in temperature, need to be able to resist all the geophysical hazards that they may be confronted with, and so on. And there are different types of lunar habitats, and here I'm presenting just some proposals that are typical of inflatable structures, some rigid structures, and this is the particular type that we are focusing on today, which is 3D printed structures. And 3D printed has a number of advantages, including its very neat or very precise use of in situ resource utilization frameworks, because it lends itself very easy to that. You require a minimal transportation of materials from Earth, and you can create virtually any shape depending on the constraints of your constructive or your construction robots. Yeah, but when we are talking about arches, one of the problems that we have is that we also have limited gravity or microgravity environments. So those arches that on Earth will be resisting both gravity and seismic loads, mainly due to their inertia, will be relatively more prone to instabilities on the moon, just because they are lighter. So we looked at ways to optimize those arches, and you can see here, for example, a naturally formed arch where the bits of material that are under less compressive stresses have been eroded with time, and then you are left with a shape that resembles a thrust line or so. And this comes back, of course, to the idea of Robert Hooke, that as hangs a flexible line, so but inverted will stand the rigid arch. And the idea is that if we are able to fit that, what he thought it was a catenary, but then was demonstrated by Milankovitch not to be a catenary. But if we fit that curve within the constraints of the depth of our arch, we should be talking about stability. We should be ensuring stability of our arches. And we devised a numerical procedure to solve this set of equations, and also to be able to search optimal forms. So basically, we have the vertical gravity thrust line, and in this case is a lateral thrust line associated with seismic loads. And then we need to invert or mirror that lateral thrust line, because the seismic event or the seismic load can come from different directions. So having those three thrust lines, we can take away all the material that is not necessarily needed outside the area that they cover, and then we can rerun this process several times in order to get the optimal result. And the optimal results that we are getting have more or less this form. We then 3D printed some samples here and tried to quantify the forces, or in this case, the degree of inclination of the supports at which instability will ensue. And then it needs to go through a process of rationalization where we are looking at the constraints on the thinner areas of it, so that it becomes actually able to be fabricated and so on. But these are more or less the shapes of optimal arches that we are getting with this mechanical procedure or mechanistic thinking. Then we thought with Jad and Milad from NASA, what about the use of machine learning in these cases? And we tried to explore the extent to which machine learning or AI in general can help us to understand the range of possible designs that we can achieve within the context of this provision of extraterrestrial shielding structures. So what we are doing here is employing an autoencoder architecture, which takes a given input arch image and fits it into an encoder. This encoder will reduce the dimensionality of, will progressively reduce the dimensionality of this image, producing a latent space at the end. Yeah, and later that latent space will be used by a decoder model that will take it and will attempt to reconstruct the original image. Yeah, so this is done in this case by a series of convolutional layers, max pool layers, and in the case of the Vcoder, we are using upsampling and deconvolution to get back to the original, or as close as possible to the original image, and then compare that and train our network. So all these spaces, all these steps are carried out sequentially to produce these finally reconstructed images. So in order to train this model, we created several data sets. One important consideration was the ability or the possibility of including within our data sets those arches that we would have considered optimal if we were using just mechanistic principles and thinking, but also try to expand the range of arches that we are looking at, just in the case that we may be looking or we may have overseen some other potential optimal configurations. So at the end, we parametrized the formulation of the shapes. It's defined by between 5 and 9 different parameters, or 12 parameters of thickness and radius, and these include very odd-looking arches, as you can see here, just because we wanted to investigate how the model is able to pick up different features and group them together according to their shape. Yeah, and maybe to try to extrapolate or to go beyond what would be influenced by our own intuition, structural engineering intuition. And we created models that were then run in Abacus to come up with some stress contours and deformation fields. We use Latin hypercube sampling to try to get a reasonable amount of data points. And these are the mechanical characteristics of the regolith that we are using. The regolith, by the way, is the soil that is found in the upper layers of the moon or Mars. In this particular case, we are using a lateral force equivalent to an acceleration of 0.2 times the gravity on Earth. That's following some advice from our seismologist in the team. Yeah. So then we run the images through the encoder. That reduced their dimensionality, as I've mentioned, and each latent space vector corresponds to one of the images. And then we take this latent space to the decoder and try to reconstruct those images. And then we quantify the loss between the calculated or the original input and the reconstructed image. And then this process is repeated several times in order to minimize that loss, changing the weighting of our networks. So we then did some random works, as you can see here, using k-means clustering, just to see whether we can identify clusters of arch shapes that have particular behavioral characteristics, and we did manage to get that. So you can see, for example, here that if we are looking at the 26th vector here, we will have arches that are thinner, whereas here we will have a more bulgy arch at the top, especially, right, at the height of the crown. So we did gain a better understanding of the effect of different latent space dimensions on the produced arches. We also carried out some actual dynamic analysis using, in this case, pulses, and running those dynamic analyses to come up with a final envelope that will characterize in summary, all the performance or the structural performance of our arches. And at the end, we tried to use this Bayesian optimization. We actually did use the Bayesian optimization to formulate a multi-objective optimization framework that takes into account both the occupancy, which is a measure of the amount of material that we are using, and also maximize the distance to grade, basically trying to make the arch as safe as possible with different weightings here. And as I said, the occupancy is a measure related to the area of the arch, and that will change between 0% and 100%. And the distance to grade is a more structural related parameter. So it quantifies the distance to stress that will signify failure, for example, or a limit in our deformation capacity of the material, which is quite fragile, to be honest. So what have we learned from the use of machine learning in the design of these lunar structures? So to sum it up, we have seen that the autoencoder was able to pick up and categorize features from the arch data set that would have been extremely difficult for a human engineer to do. Now, the required latent space dimensions will depend on the number of distinct arch shapes that we have. We also built a regression model that I've not spoken here today, but this allowed us to get outputs with a given set of input geometric variables. We were very interested in moving in the latent space and try to identify how that governs the output arch shapes, both in terms not only of the shape, but also in terms of the stresses and strains that we get. And it was actually very informative, this stage, basically because you are dealing with a reduced dimensional space, which would otherwise be unmanageable by our minds. At the end, the arch is obtained by the mechanistic thinking, the first part, the related to the work of Tom, related to thrust line analysis and limit analysis and so on. Those arches are actually very similar to those arches that were generated using the machine learning approach, but they are not identical. And especially when you start including dynamic loads, it is much more difficult to find out a mechanistic algorithm that will optimize proper dynamic results, right? So there is some advantage there. And this leads me to the exploration of these areas of creativity and intuition, because what we have seen from the manipulation of the latent space dimensions in this case study is that we were able to understand a bit better what are the influence of different dimensions on the structural performance, and therefore guide our design. It may not be taken over completely from us because we were at that stage guiding the design, but it can in the future, as our optimization algorithms become better suited for that, it can take over. So this issue of modeling the human intelligence on the perceived way we process and understand information has actually led to remarkable tools that can really boost our engineering design capabilities, and allow us to operate on large data sets and make even more accurate predictions of response and performance. But understanding and reasoning through the mechanistic aspects of our problem are not the only ways, and perhaps not even the most frequent ways in which engineers solve their problems. Yeah, intuition that we can understand as a form of recognition, or the ability to understand something almost instinctively without resourcing to reasoning, plays an important part in the engineering decisions. In fact, engineers who may prefer to call it judgment use intuition or engineering judgment, even when they are developing computer models, just to select, the type of connections that they are going to be using, the type of elements, the configurations, what are they going to left outside, and what they are going to actually model within their FE. So that's an important recondition that we need to have. Creativity, on the other hand, is also usually defined as a potential area where we can use AI to enhance our creative endeavors. The problem with creativity is that it tends to be a bit more subjective. And I think that is, it really has to do a lot with the way in which it has been presented, especially in the context of the ICEF2023 training demands that I was discussing before, or what is perceived as a new way in which we should train our engineers, because you can play on this subjectivity to get away from the more measurable and actually declining mathematical skills. So creativity is usually defined as the generation of novel and useful ideas, but that immediately invokes the existence of somebody or a person to whom that idea, that structural design, would appear as novel or useful. Yeah, so you understand this subjectivity, and the way it has been pitted against the more quantifiable and, I repeat, declining numerical skills. However, this subjectivity doesn't need to be there, because creativity doesn't fall from the skies. Is actually emerging not in the vacuum, but it's actually emerging from a context. Yeah, and it will appear that if we have access to that context, then we should be able to train our networks to understand that context and reflect that. And in fact, that has already been done in the provision of, for example, some 3D structural configurations by other authors. Yeah, so in the structural engineering field, a relatively similar approach to that I was referring to before has been attempted by the group of Professor Muller in the MIT, where and also now Professor Carstensen from Josephine from the MIT as well, where they are exploring how to use optimization algorithms in order with the interaction with in interaction with the human engineer to be able to design better our infrastructure and our structures. So they are allowing the design engineer to have access to a family of being 2D latent spaces or being topological optimization dimensions. And this feature is actually encouraging, and I think it encourages designers to investigate different trade-offs between different design features that would have otherwise remained unexplored. And it really opens the door for a more integrated machine designer collaboration, right? That I think is actually the future. So it would seem that there are yet many routes that we can take to encourage the creativity and probably reinforcement learning approaches are one of those areas that is that can be very positively used in this regard. So what do you think? Thank you very much.